So the daily problem is pretty interesting. Implement a queue using stacks. And it's really satisfying because you can immediately understand the conceit of the problem. A queue is first in, first out. So your operations with a queue are push to add an element to the queue, pop, which removes and returns the first added element that hasn't been removed yet. Peak, which shows this, and those are the most important ones. And a stack is the exact same thing, except it's first in, first out. So you can think of this sort of like a cup or a bucket, and you're putting things in on top of the previous stuff, and in order to get at that stuff, you have to take the top thing out first. And as a side note, stacks are always depth first search, queues are always breadth first search. That's sort of an association that's good to have. So a stack, you can kind of think of like a bucket where you're stacking things up, and a queue, it's all like a line of people in a fast food restaurant or something. But what we have is two stacks, and we want to simulate a queue. And I like this problem because there's a couple different ways to do it, of varying degrees of efficacy. And they even say in the bottom follow-up, can you implement a queue such that each operation is amortized to O of 1 time complexity, which seems just outright impossible, because O of 1 time complexity, that's something like an array lookup, or if you're using hashing in like a set or a hash map, that would be, accessing an element with a key. We don't have anything like that with a stack. If we have a bunch of stuff, all these things, and we're putting things in the top, it's actually the polar opposite of this is the worst possible thing we could use potentially, or on its surface, because what we want is the very bottom thing. And that does offer up an immediate solution that doesn't really follow with this follow-up, but this isn't easy. So the first solution to implement is just, all right, well, we need that. What if we just use the second stack as kind of temporary memory? We put everything in the first stack. We ignore the fact that we're trying to treat it like a queue. And then as our kind of custom stack pop function, we say, all right, we'll put all this stuff in this stack. Who cares? Pop this one, or peek it for peek if we're just looking at it, and then put everything back from this stack back on top. And it retains the order. And that's pretty, I think, elegant in a way. I mean, it's O of n time complexity, where n is the length of the stack every time you have to peek or pop, which is really inefficient, but it's a good place to start. So let's reset to the default code. All right, in it, we got self.st. Let's say st1 is, we're going to use dequeues. Self.st2 is a dequeue. Push, very simple. Self.st1.append x. Pop is a little more complicated. Peek is a little more complicated. Empty is also pretty simple. That's just return not self.st1, which means if we just said return self.st1, what this would mean is, hey, treat this like a Boolean value. Treat this stack like a Boolean value. And the way that Python interprets that is it says, does it have a length of 0 or does it have a length of more? So this would be, hey, there's something in the stack, which means that not st1, there's nothing in the stack. So then self.pop, we want to say, all right, well, one way to do it would be while self.st1, again, treating it like a Boolean, saying as long as there's anything in self.st1, we can say self.st2.append, so add to self.st2 the top thing popped from self.st1. So what this will do is it'll say, hey, while there's anything in here at all, put it in here. So then what'll happen is it'll put in this one, and then it'll put in this one on top of that, and then this one on top of that, and this one on top of that, and what we'll wind up with is exactly a reverse order, which is what we want. And then we just say, oh, cool, okay, then the value we want to return, let's say and, is self.st2.pop, So that would be the top thing in ST2 or the bottom thing in ST1 originally, and then we just put everything back in ST1. So we say, well, self.st2, self.st1.append, self.st2.pop. And then we pretty much just do the exact same thing for peak, except we say, oh, and then return ands. Except here we don't say pop, we just say st2 at -1, aka the last element in st2. So when we run this, it should just kind of work. If this was a more complicated problem, this wouldn't pass the time complexity, because you can do better than this, and usually mediums and hards don't let you use a suboptimal algorithm. So this is a good place to start. I mean, this is how you pass it if that's all you're here for. But we can improve on this significantly, and that's where it gets really interesting. And I'm kind of proud of my solution. I assume it's the solution, but I didn't look anything up. I just thought it off the dome. So for what that's worth, but let's reset it again and get our stacks back. And I'll just copy that one. So the thought process is, again, how do we simulate a queue with this? How do we access that bottom variable without direct O of 1 access like we would have in an array or a hash map or something? How could we possibly do that? And I think an immediate intuition is we don't get direct access. And they even hint in that in the problem that they specifically say in this hint, like, oh, well, it's amortized time complexity. In other words, performing n operations will take O of n time, but one operation might take a lot longer, which is our first hint, or that's the hint here. And so the question is, all right, well, what might an operation look like that takes a lot longer, that takes O of log n, or takes O of n, or takes O of n squared? What does that look like? And we can kind of refer to what we just did. What happens if we put everything in here? Well, we put the top one in the bottom, we put the second to top above that, we put the third to top above that, and again, you know, just like before, we get this exact reversal of this stack into this stack. So in a way, then this stack is kind of the output stack, because then the top thing here, whether we're popping it or peaking it, is always going to be what we want. And if we think about it, the next time that peak or pop is called, it's just going to be this again. If the last thing was peak, or if this was popped off, then it's just going to be the thing below it. And we don't have to do anything if that's the case. So if we can find a way to have this stack retain this memory, then we're actually just good to go. As long as this stack is full, we don't actually have to empty it back into this stack ever. We don't ever have to do that. We can just say, like, well, it's already here, this can just be our answers stack. And then we just say, like, this one fills up over time, and then the moment that we call pop or peak, we just pop one off here. And then we can just say, hey, if this is empty, that's why this stack exists. Just put everything in here into here. And the idea is, this is an O of n operation to put everything from this stack into this stack. That is O of n, where n is what would that be? That's the thing. The number of times that you would do that, like n is the number of items in this stack at that point. But this wouldn't equal the number of elements that have been put into this simulated queue, because you're only removing elements from the stack over time. So this is going to be far less. This is just a cache, and the only time that things are put from here into there is when this is emptied. So in the beginning, potentially, but also, let's say you have 2 elements in here, 0 in here, peak is called. Then it's going to say, all right, well, put these 2 elements in here. This is now empty. Great, who cares? This now has those 2 elements reversed, And then we say, all right, peak this. Let's say pop is called, pop this. So then we have 0 and 1. And then let's say pop is called again, so it's 0 and 0. And then let's say push is put twice. There's 2 in here. And we can repeat that. Or, yeah. And the idea here is that this is going to bottom out on average, assuming that push and pop are called relatively in the same amount of time. That's only going to be called once every O of n operations. So we have this situation where, every O of n base operation. So we have the situation where this operation we're sort of imagining of dumping this stack into here is an O of n operation to do that, which is not what we're aiming for. But then it only happens once every n times that it needs to happen. I believe that's at most. That's worst case scenario, but I might be wrong on that. At the very least, it's amortized to that. And what this means is really what's happening is this is just O of 1. And this actually is how a lot of languages do things like lists, when they say stuff like, the moment you reach capacity, just multiply the capacity by 2, and that's an O of n operation, but it happens a diminishingly small amount of times. So realistically, for those data types, like a list or an array list or something like that, it's really just, it amortizes to O of 1 to append a new thing, even though there might be some times where appending a new element to a list and increasing its capacity is O of n, it amortizes to O of 1. So what we've outlined is this sort of new function, new operation refill. And what that's going to look like is just dumping all of st1 into st2. So we just say like while st1, let's say self because it's Python. And then this is actually quite simple. It's just st2 dot append st1 dot pop. So we're just dumping everything in there. And then we can refer to that in pop and peak. So for pop, we eventually what we want to do is we want to say return self.st2.pop. And for peak, we just want to say return self.st2 at -1. And then we say, well, what if st2 is empty? I think it says all calls to pop and peak are valid, so we don't have to worry about a situation where we have to throw an error. We know if st2 is empty, then st1 is not empty. So then we just say, all right, well, if not self.st2, self.refill. And we can literally just copy paste this to peak as well. And then empty, we say, well, if st2 is empty, if not self.st2, then we need to know if self.st1 is empty. If both of them are empty, then this is completely empty. Actually, we can literally just say that, I believe. We can just say return not self.st2 and not self.st1. And then push is really simple. That's just self.st1 dot append x. Cool. Hopefully it all just runs and there's no debugging. And it does. We can see that this is somehow a lower percentage than our other algorithm that we just submitted. But that's the random variance on their end. This would be faster if you were if you ran it 100 times, or if you had more stringent test cases too. But yeah, we look at it and push is O of 1, and it is O of 1. That's just making 2 DQs. Refill is O of n. Pop, we say if not st2, then pop is O of n. Otherwise, it's O of 1. Same with peak. Empty is O of 1. And, I sort of, in layman's terms, outlined how this amortizes to O of 1 rather than O of n. But the basic gist of it is that a situation where not st2 comes about only comes about once every n, in quotes, operations of pop. And with peak, it's even less so. If we only had peaks, then this would just always be O of 1. Yeah, so self-refill is only called once every n times, so even though it's O of n, really it amortizes to O of 1 if you average it with all other operations. So I just wanted to show that. I think that's a really interesting, fun problem. The easies are always satisfying when there's a harder iteration on them.